In this lesson, we want to talk about parallelograms. Some of the things we want to do in this lesson, we want to be able to recognize and apply properties of the sides and angles of parallelograms. And we want to be able to recognize and apply properties of the diagonals of parallelograms. We've got some new vocabulary here that we need for this lesson. Quadrilateral. We talked about these briefly in the last lesson. When we talked about polygons, we studied polygons with all different numbers of sides. And a quadrilateral, we learned, was a polygon with 4 sides. And in this lesson, we want to study a very specific type of quadrilateral called a parallelogram. Parallelogram is a quadrilateral with parallel opposite sides. That's our most fundamental definition of a parallelogram. Now, there's lots of other interesting properties about parallelograms, just like we learned if we knew we had a triangle, there were other things that we knew about triangles. For instance, we knew that the sum of the interior angles was 180 degrees. Parallelograms, being a quadrilateral, we know the sum of the interior angles is 360 degrees. And there's also lots of other interesting things that we know. We know that if a quadrilateral is a parallelogram, then its opposite sides are going to be congruent. You can see they're marked here. JK is congruent to ML, and JM is congruent to KL. And we can prove this really quickly, actually, with some Legos. We can take, here we've got 2 Legos that are congruent to one another, and 2 other Legos that are congruent to one another. So if I try to assemble these into a parallelogram, you'll see that in order to get this parallelogram to close with these opposite congruent sides, the sides must remain parallel when I do that. And you can see, you can adjust it. It can collapse and it can expand. And this is interesting because the other polygon that we spend the most time talking about in geometry is the triangle. And this is how triangles and parallelograms are very different. If you want things to move, then you want a parallelogram. If you want things to not move, you can draw one of the diagonals in a parallelogram and you end up getting 2 congruent triangles. And triangles are what you want when you don't want things to move. Once I draw that diagonal, you can see my structure no longer moves. So for civil engineers, this is great. We build with triangles so that our trusses and our buildings and our bridges don't move. If, however, you're a mechanical engineer, you may want things to move. And an assembly like this could be very useful in something like a scissor lift or a jack or something like that. But that kind of demonstrates this property right here, that if our quadrilateral is a parallelogram, we know our opposite sides are going to be congruent. Another thing we know is that if our quadrilateral is a parallelogram, then its opposite angles are going to be congruent. Angle M is congruent to angle K. Angle J is congruent to angle L. And we know this because, well, if this is a parallelogram, our fundamental definition tells us that the opposite sides are parallel. So JK is parallel to ML, and JM is parallel to KL. And from chapter 3, we learned about parallel lines. We learned that I could extend this line right here, and I could look at these 2 parallel lines in ML as a transversal. And so I could say that this angle here must be congruent to angle M because they are corresponding angles. And then I can look at extending this line here and say, oh, now I'm looking at these parallel lines with this transversal. And I know these angles will be congruent to one another because they are alternate interior angles. So that proves what we suspect here, that these opposite angles in a parallelogram are going to be congruent. And likewise, we could extend the lines and prove the same thing with angles J and L. Now, another thing we learned from our lesson on parallel lines was that consecutive interior angles, when lines are parallel, consecutive interior angles will be supplementary. So that brings us to 6.5. If a quadrilateral is a parallelogram, then its consecutive angles are supplementary. That means any two angles in a row. So x and y here, x plus y will always equal 180 if this is, in fact, a parallelogram. Because you can see here our parallel lines and our transversal. That makes these two consecutive interior angles. Likewise, M and L are also consecutive interior angles, and that means they are going to add up to 180 as well. And lastly, we have 6.6, which tells us if a parallelogram has one right angle, then it has four right angles. And that means that your parallelogram happens to be a particular type of parallelogram called a rectangle, which we're going to study more later in this chapter. In this, you can quickly prove, same way we proved 6.4. Or if you know you've already proven 6.4, then J and L must be congruent. Those must be 90. And we've already proven this one, so we know that angles M and L must be supplementary. So that means M must be 90 and K must be 90. Let's take a look at a couple of examples. Here in parallelogram ABCD, and make note when you see this in the text or in a problem, that symbol right there means parallelogram. Okay, that's a parallelogram. And in parallelogram ABCD, suppose that the measure of angle B is 32. I'm going to go ahead and label that 32 degrees. And CD is 80 inches. 80 inches. And BC is 15 inches. Okay. And what I want to show you here is that when you know something's a parallelogram, there's a ton of other information that you know that you can fill in to solve your puzzle. They want us to find AD. Okay. And you're probably already looking at it and saying, oh, I recognize one of those properties. This is a parallelogram. Opposite sides are going to be congruent. And that means if BC is 15, AD is also going to be 15. How long is AB going to be here? Well, again, the opposite sides are going to be congruent. So AB must be 80 inches. Now, what would you say the measure of angle D is in this diagram? If it's a parallelogram, we remember these opposite angles are congruent to one another. So angle D must also be 32. Now, could we find angle C? You may recall that angles B and C are consecutive interior angles. So 32 plus x, let's call this x, must equal 180 degrees. And we can solve for x by subtracting 32 from both sides. We get x equals 148 degrees. So if you know something's a parallelogram, there's a ton of other information you know that you can fill in to help you solve whatever puzzle you're looking at. Let's take a look at another one. Here, ABCD is a parallelogram. Could we find AB? Well, if this is a parallelogram, then opposite sides are congruent. And we can see that AB is going to be 30. How long would AD be here? Again, opposite sides are congruent in a parallelogram. So AD is going to be 20 units as well. What would the measure of angle C be here? If it's a parallelogram, our opposite angles are going to be congruent. That means angle C must be 36 degrees. And could we find the measure of angles B and D? Well, if angle D is x, you know angle B must be as well. And we also know the relationship between angles C and D. These are consecutive interior angles. So 36 plus x must equal 180 degrees. And we can subtract 36 from both sides of that equation, and we get x equals 144 degrees. Okay, there's a couple other things that we know about parallelograms. If we draw the diagonals in a parallelogram, then the diagonals are going to bisect each other. So, in other words, AP here is going to be congruent to PC. And PD is going to be congruent to PB. Okay? And if you draw one diagonal in a parallelogram, like I suggested earlier with the Legos, if you draw one diagonal, then you actually separate the parallelogram into two congruent triangles. And this should make sense because we have AB congruent to DC, AD is congruent to BC, and we can see that BD is congruent to itself. And so you might recognize that these two triangles are congruent to one another using side, side, side. Okay. Let's see what else we got here. That's where the two-column proof. If we're given that this figure is a parallelogram and that AC and BD are diagonals, point P is the intersection of AC and BD, could we prove that theorem that we looked at earlier, that AC and BD bisect each other? Okay, we want to prove that, ultimately we want to prove that AP is congruent to PC and DP is congruent to PB. Okay, so two-column proof, we're going to make some statements, and we are going to have to give each of our statements a reason to justify what we know. Okay. And can we mark what we know? What would be helpful here in proving that these diagonals bisect each other? Well, I see 4 triangles when you draw the two diagonals. And I suspect that some of those triangles are going to be congruent to one another. And if I knew that, I think I could prove that perhaps this side is congruent to this side, and this side is congruent to that side. So let's take a look at that. I think we know that AD is congruent to BC. We could say that AD is congruent to BC. And the reason is, that is one of our properties, you could say definition of a parallelogram. When you know something is a parallelogram, you have all of this free information that comes along with it. So we have that. We also know that AB is congruent to DC. AB is congruent to DC. And again, that's our definition of a parallelogram. Okay, I think we also know something about these sides being parallel to one another. I think we could say that AD is parallel to BC. It's also one of our defining properties of a parallelogram. And we could also say that AB is parallel to DC. AB parallel to DC. Okay? If we know those lines are parallel, now I'm starting to look at some angles here. I see this angle here, and I think it's going to be congruent to that angle, because those are, let's see, angle ADC is congruent to angle CBD. And the reason is, those are alternate interior angles. And we know that alternate interior angles are congruent when the lines that form them are parallel. Okay. And likewise, I think I could claim that this angle is congruent to this angle. So I could say that angle DAC is congruent to angle BCA. And the reason is, those are also alternate interior angles. And now I'm looking at this and I see congruent triangles. I see this triangle right here, ADP, and I see that it's congruent to that triangle right there. How do I know that? Do I have enough information? And say triangle APD is congruent to triangle CPB. And the reason is, angle, side, angle is congruent to angle, side, angle. Okay? Now, if I have that, I can go ahead and say that these segments are congruent. How do I now know that DP is congruent to PB? Because corresponding parts, congruent triangles are congruent. CP, CTC. We remember that from chapter 4, hopefully. And likewise, I know that AP is congruent to PC for the same reason, because corresponding parts of congruent triangles are congruent. And once I know that these two segments are congruent, then I can declare that AC, again, looking back at what we were being asked to prove, our goal, AC and BD bisect each other. And the reason is, that is our definition of a bisector. If this segment cuts that segment into two congruent parts, it must be a bisector. Okay, not too bad. That's one of the more involved two-column proofs that we'll do. But it's good to know that when we have these theorems and definitions, we can prove them, and a lot of it builds on everything we've already learned here in terms of congruent triangles and parallel lines. All right, let's take and do a couple of other problems. If we have this sketch here where WXYZ is a parallelogram, could we use what we know about parallelograms and their diagonals to find the value of R, S, and T? And the first one I want to go after is R. You might notice that WX here is represented by this expression 4R. If this is a parallelogram, I know the opposite sides are congruent. And there we should be able to find an equation. 4R must equal 18 if this is a parallelogram. And we can divide both sides by 4. We get R equals 4.5. Now, let's take a look at S. We've got this expression here representing this segment, and this expression representing this segment. We know if this is a parallelogram, these diagonals bisect each other, and these two segments must be congruent. So that gives me another equation. 8S must equal 7S plus 3. And I could subtract 7S from both sides, and I'm left with S equals 3. Good. Now T is part of this expression that represents this angle here. And if this is a parallelogram, and these sides are parallel, that makes these two angles congruent to one another. Oh, excuse me, I got the wrong angle. That makes these two angles congruent to one another because they are alternate interior angles. So I can see that 2T must equal 18 degrees. And I can divide both sides by 2, and I get T equals 9. Okay? Let's try one more of those. And if we are given parallelogram ABCD, could we find the value of these variables here? If this is a parallelogram, we can see that these diagonals must bisect each other. And hopefully here you're finding an equation. This expression must equal this expression because these two segments are congruent. So we should get 4x plus 12 equals 6x plus 2. Good. We can solve this for x by subtracting 4x from both sides, while we subtract 2 from both sides at the same time. And we're left with 10 equals 2x. Divide by 2, and we will get 5 equals x. Now, how about k? K here is in this expression, which represents this angle. And I think if these sides are parallel, so they must be, it's a parallelogram, then that angle must be congruent to this angle down here because they are alternate interior angles. So I get another equation. 3k plus 4 must equal 25. And I can subtract 4 from both sides. And we get 3k equals 21. When we divide both sides by 3, we get k equals 7. And lastly, we've got p. P is in this expression here, which represents the length of side AB. And I know if it's a parallelogram that these opposite sides must be congruent. So 2p must equal 22. And I can divide both sides by 2, and I get p equals 11. Okay, let's try one more problem. Last problem in this lesson. We're going to do a little bit of graphing. This problem is asking us what are the coordinates of the intersection of the diagonals of a parallelogram MNPR with these vertices. Okay, let's go ahead and just establish ourselves a coordinate plane here. And let's plot these points. And M is at -3, 0. Okay, you should be in the habit of labeling your points when you plot them, because those coordinates, we're going to work with them. We're going to use those numbers. And N is at -1, 3. Here's N, -1, 3. P is at 5, 4. Over 5 and up 4. Gets me point P right here. And R is at 3, 1 over 3 and up 1 from the origin. Gives us point R. Okay, and there is our parallelogram. I want to know what are the coordinates of the intersection of the diagonals. Well, what do we know about diagonals and parallelograms? If you want to draw them, you can, so that you can graphically get a good idea of where these are going to intersect. Now, graphically, you might look at that and say, it looks like 1, 2, but algebraically, how could we prove that? How do we know that it's not slightly off? That point right there. Well, we know the diagonals bisect each other. So could we use our midpoint formula to figure out what the exact coordinates of that point are? You might remember our midpoint formula. Midpoint is, we'll take the x-coordinates of our line segment and the y-coordinates, basically finding the average of each one. So we could call this x1, y1, and this x2, y2. And if we find the midpoint of that diagonal, we'll have the exact coordinates. So let's go ahead and plug that in to our midpoint formula. -3 plus 5 divided by 2. And let's plug in our y-coordinates. 0 plus 4 over 2. Okay, and when we simplify that, we're going to find -3 plus 5 is 2 over 2. Gives us an x-coordinate of 1. 0 plus 4 is 4 divided by 2 is 2. So you can see, graphically, we have a good check on our algebra here. The intersection of the diagonals occurs at x equals 1, y equals 2. All right, that is our lesson on parallelograms. I hope you found it informative. And don't forget all of the properties, all the things that you know if you have a parallelogram. You have opposite parallel sides. You have opposite congruent sides. You have opposite angles congruent to one another. You have consecutive interior angles that are supplementary. And we also know that the diagonals bisect each other. And from this, there's a whole lot of problems that we can solve in geometry.